Continuing with Chapter 10, we're going to talk about the ladder of powers. There is a family of simple re-expressions that move the data toward our goals in a consistent way. This collection is called the ladder of powers. So what the ladder of powers does is it orders the effects that the re-expressions have on the data. This is a ladder of powers. I recommend that you pause now and copy this down. I would leave room to write examples or maybe add something that I say that's not listed here in this table. The ladder starts at a power of 2. Think of the powers as an exponent. Now, we're always going to start by re-expressing our y variable. So a power of 2 means that would be y to the second power, or y squared, which is why the name is a square of data values. This is often helpful when the data is unimodal and skewed to the left. So if it's skewed to the left, that means the majority of the data are higher data values, and then you have some that are a bit smaller. A power of 1, so a power of 1 just means that the data is what it is, which is why it's just our raw data. So it doesn't necessarily need to be re-expressed. We're good, that's where we start. So your data starts out right here. A power of 1/2, so if you raise something to the 1/2 power, that's the same thing as taking the square root, which is why this would be the square root of your y values. Counts often benefit from a square root. So counted data, for example, if we were monitoring the migration of penguins. So maybe we're looking at how many times they come to a specific site, depending on temperature. So we would be counting how many penguins there are. If that's not a straight data, then we would take the square root. A power of 0 is what we use for a logarithm. So this would just be taking the log of your y variable. So measurements that can't be negative often benefit from a log. Also, large values benefit from a logarithm. So if you're talking about populations or salaries, those are good things to use a logarithm for. The power of a -1/2 is the reciprocal square root, so 1 over the square root of y. This is an uncommon re-expression, but can be useful. And then the power of the -1 is like the inverse or the reciprocal of the data, so you flip it. This is good if your units are a ratio of two quantities, so miles per hour, gallons per mile, any ratio. Now this is the one that will change the direction. If you don't like the fact that it changes direction, what you can do is you can do the negative reciprocal, and instead of 1 over your data values, you could do -1 over your data values, and then in that case it will keep the same direction. So if you want to keep the same direction, instead of doing 1 over, just do -1 over. The ladder of power puts everything in order by strength. So if you have one and it seems like it's too strong, you can always move back down the ladder to try a different one. However, if you don't know where to start, you want to start at 0. Start with a logarithm. That 0 power is kind of the middle ground, so if you don't have any other ideas, start with a logarithm. That would be where to start. When I'm talking about strength of the ladder, I mean, if you try a re-expression and it curves it in the other direction, it's too strong, so you might want to move back up the ladder. If you try and re-express your data and it's less curved but still slightly curved in the same way, you may want to move further down and try another re-expression. The other thing is to think about what your scatter plot looks like. Taking the square of all of your data values, if your data appears to have a square root graph, so it starts and it kind of curves up and then levels out, squaring all of your data values may straighten that out. Same thing if your data values look more like a parabola or half of a parabola, taking the square root may help straighten that data out. Logarithms and exponential functions are also inverses. So if it looks like you have an exponential function where it's increasing really quickly, you might try a logarithm to straighten that data out. So think about what type of function the graph may look like and try the inverse function of that. So square roots and squares and logarithms and exponential models. So plan B, attack the logarithms. Sometimes none of the re-expressions on the ladder work. That can be a problem. So we go to plan B. So when none of your data values are 0 or negative, logarithms can be helpful. If you have a data value that is 0 or negative, you cannot use the logarithm because you cannot take the log of a negative number. But by trying to take the log of both the x and y variable, it can often help re-express it and make it straight when nothing else worked. Then the re-expression of the data using some combination of x or the log of x versus y or the log of y can also be helpful. So I have a table of this right here. So if, again, the model is looking like it's an exponential model, just follow the ladder and try the log of just your y values. If the model looks to be logarithmic, which means it kind of is curving downwards instead, try taking the log of the x values. So this says that a wide range of x values or a scatter plot that descends rapidly may benefit from this. And then when pretty much nothing else works, try the log of both. They call this the Goldilocks model because it means that you tried something on the ladder and it was too big, so you went to the next one and that was too small, so this one may just be right. But sometimes, if all else fails, try the log of both. Re-expressing data has multiple benefits. We often choose a re-expression for one reason and then discover that it helps in other aspects of the analysis. So it may make the distribution shown on a histogram more symmetric. And it also may make it so that our scatter is more consistent, so you have less variance in that situation. But why not just use a curve? If there's a curve, just put a curve to it. The problem here is that the mathematics for a curved calculation or curves of best fit is a lot more difficult. It's more difficult to do, and it's more difficult to interpret. Straight lines are easy to understand. We know how to think about the slope. We know how to think about the y-intercept. But as soon as we are changing slope to just a rate of change, which changes from data value to data value, it's hard to think about that. So we like to keep things straight. So what can go wrong? The first thing is that you expect the model to be perfect, and it won't be. Okay, we're re-expressing it. We're trying to make it more straight, more nearly linear. So it's not necessarily going to be perfect, and that's okay. You also don't want to stray too far from the ladder. Don't start trying to do weird things. Stick to what we know. Try and manipulate the y variable when nothing else works. Try taking the log of both. And then don't choose a model based on your r-squared value alone. So when you calculate that new equation and you see your r-squared value, just because it's a high r-squared value does not mean that the data actually works. You have to check the residual plot because sometimes the data can look like it's going to be really straight and it's going to have a high r-squared value. And you go and you check the residual plot and you still have a clear curve. That's an issue. So then you have to go back to the drawing board and try again. A lot of this is going to be guess and check. We'll go over where to start and what the best aspects are, but a lot of times you're going to try it, see if it works. If it doesn't, move on to the next one. And then finally, what have we learned? When the conditions for regression are not met, a simple re-expression can help. So a re-expression helps make the distribution more symmetric, spread similar across groups, makes the data straighter, which is what we're really looking for, and it makes the scatter more consistent, so lessening our variance. And finally, we also learned that taking logs is often a good starting point. So to search further the ladder of powers or the log-log approach can help us find a good re-expression, but starting off with a logarithm is often a good place to start, and then seeing where we go from there. Our models won't be perfect, that's okay, but it is helpful to re-express the data so that we can use a linear model. That is it for Chapter 10. We are going to practice using the ladder of powers in class, and we'll go over how we can mathematically re-express this data using our calculators so you won't have to do it all by hand. In fact, you'll do very little of it by hand. Other than that, that's it for tonight, and I will see you guys tomorrow.